All right, let's dive into a new paper from DeepSeek that is getting a ton of attention. People are calling it a potential game changer because it proposes a totally new way to wire up large language models, and honestly, it might just change everything. And no, this is not just some tiny incremental update. The hype around this is very real. Some are even saying this could be the driver for the next major AI breakthrough in 2026. So, what is all the fuss about? Let's find out. So here's our plan. We're going to start with the absolute bedrock of today's models. Then we'll look at a really cool new idea that tried to improve it, but oops, it had a hidden flaw. And finally, we'll get to DeepSeek's brilliant solution and see the results to back it all up. The paper at the heart of all this is called MHC, Manifold-Constrained Hyperconnections. Now, this didn't just appear out of nowhere. It actually builds on a 2025 paper from ByteDance, taking a really promising idea and, well, making it actually work for huge, massive scale models. But, to really get why this is such a big deal, we've got to rewind a bit. To understand where AI is headed, you first have to understand the foundation it's been built on for almost a decade. And for what feels like forever in the AI world, the past, the present, and pretty much the future has been completely dominated by one single concept, the good old residual connection. And just look at this timeline. It really shows you how long this one idea has been king. Way back in 2016, ResNet introduced it to fix vanishing gradients. That's a nasty problem where the learning signal just poof, disappeared in really deep networks. And for nearly 10 years, this design was the foundation for basically every LLM you can think of. We're only just now seeing the first real attempt to evolve this core piece of the puzzle. So, what is a residual connection? The best way to think about it is like an information highway with a special express lane. The main traffic, the data, goes through a processing block to get transformed. But a perfect, untouched copy of that original data gets to take a shortcut, a bypass, and then it's added right back in at the end. Okay, so here's how it actually works, step by step. Your input signal, let's call it X, splits in two. One path goes off to get processed by some function, think of an attention block. The other path, the residual stream, is left completely alone. It's the express lane. Then, at the end, they just merge back together. Simply adding that original, unchanged signal back in is what keeps information from getting lost and makes training these gigantic networks stable. So for years, that was it. That simple, single bypass was the industry standard. But then, hyperconnections came along from ByteDance, and it was the first serious attempt to evolve the residual connection itself. And it all started with a really simple question. If one information highway is so effective, what happens if we build a multi-lane superhighway? The big idea was to take that single residual stream and just blow it up into multiple parallel streams. Instead of one vector carrying all the original information, what if you had, say, 4 or 8? The thinking was that each of these streams could learn to specialize, maybe one for grammar, one for long-term context, one for factual knowledge, and so on. So let's put them side by side. A standard residual connection is just a single fixed path. Hyperconnections give you multiple paths, and here's the kicker, the model can actually learn how to mix information between them. That is a massive boost in flexibility and expressive power. But wait a minute, wouldn't processing 4 streams be like 4 times the work? Well, this is the really clever part. Nope. Right before the heavy-duty computation, like an attention block, the streams all get collapsed back into a single vector, and then they get expanded out again afterwards. This brilliantly decouples the model's memory capacity from its computational cost. So you've got more power, more flexibility, and no real extra computational cost. It sounds like a silver bullet, right? Well, not so fast. Turns out, all that newfound power came with a very serious hidden flaw. Instability. And this right here is the absolute key insight from the DeepSeek paper. The real magic of that original residual connection was that its information bypass was guaranteed. It was built into the architecture. It couldn't fail. And what DeepSeek realized is that hyperconnections, with all their flexibility, totally break that promise. So here was the problem. Those matrices that learned how to mix the different streams, they were totally unconstrained. They could do whatever they wanted. And because of that, you lost that guaranteed identity path. The signal's strength could either explode towards infinity or just vanish into nothing as it went through the network. And as you can imagine, that caused huge training instability, especially for bigger models. This is where DeepSeek swoops in with their really elegant fix, Manifold-Constrained Hyperconnections, or MHC. They figured out how to keep all the power and all the flexibility, but bring back that mission-critical stability. The big aha moment was this. Instead of getting rid of the flexibility, what if you could just guide it with some simple, smart rules, some constraints? It's not about having less power, it's about having smarter, more disciplined power.
Okay, so what are these constraints? The fancy term is doubly stochastic, but it's actually pretty straightforward. It just means the mixing matrix has to follow 3 simple rules. Rule 1, all the numbers in it have to be 0 or positive. Rule 2, every single row has to add up to exactly 1. And Rule 3, every single column also has to add up to exactly 1. That's it. And that mathematically guarantees that the total signal strength is perfectly preserved.
So when you put it all together, the critical difference is just crystal clear. Original hyperconnections used an unconstrained matrix, which led to instability. DeepSeek's MHC uses that constrained, doubly stochastic matrix, which guarantees stability. It's the same multi-lane highway, but now it's got smart guardrails.
Okay, so the theory is beautiful, right? The solution seems really smart, but the big question is, does it actually work? Let's check out the results.
So if you look at this table for a huge 27 billion parameter model, you can see the baseline performance right there. The original hyperconnections did give it a little bump, which is nice, but look at MHC. It's consistently the winner across the board. This proves that the constraints don't just make the model stable, they actually help it perform better. And this chart, wow, this really tells the whole story visually. This is showing the gradient norm. You can think of it as the learning signal's heartbeat. The original hyperconnect model is all over the place. These huge, scary spikes mean it's unstable. But the MHC model, it's just smooth and stable, tracking that trusted baseline almost perfectly. This is the visual proof that the constraints are working exactly as intended. So what's the big takeaway here? The success of MRH points to something really profound about the future of AI. For years, the name of the game was just go bigger, build bigger models. But this paper asks a totally different question. Will the next giant leap forward come from more elegant, intelligent architecture? Is the future of AI built on smarter constraints and not just on bigger and bigger models? That's the really exciting question this paper leaves us chewing on.